Good evening all. Welcome to the third live session on Engineering Thermodynamics for the NPTEL course. So we'll wait for a couple of minutes for the students to join and then we'll get started with today's session. I guess we can get started. Just to give a brief introduction. Hi, good evening. Okay, I guess we'll get started. I hope my screen is visible. So the first question asks you, so there is a piston cylinder arrangement shown in the figure. So this is the piston and there is a gas inside the cylinder. So I'm considering the dotted line here. Inside the dotted line is my particular system and the dotted line is my system boundary. So it says that this particular process undergoes an expansion such that PV power n equals to constant. So this is what we call a polytropic process where n can be some constant. Initially the gas is at a pressure of 3 bar. As it expands, the volume increases and pressure gets reduced. So the initial volume is 0.1 and then the volume increases, like basically the volume doubles. So the final volume is 0.2 meter cube. So you need to determine the work from the process in kilojoules for different cases for n equals to 1.5, n equals to 1 and n equal to 0. So what are these different processes? If you consider n equal to 1, that is PV equals to constant. So what is this process? That is an isothermal process. And similarly, when n equals to 0, we have PV power 0 equals to constant, which is essentially P equals to constant, and that is an isobaric process. So in this question is the same, we'll be solving in 3 different scenarios. So we'll be solving the work done for a polytropic process, for an isothermal process, and then an isobaric process. So first we'll derive the general equation for a polytropic process. So what's the equation for the work done? In a reversible process, work done is given by integral PdV, and even in the last week we were discussing that the process has to be slow. So when we are saying the process is slow, that means when we are doing this particular integration over here, the function for P has to be valid throughout the integration. So this will be valid only if the process is slow. If the process happens very fast, so for example if you pull the piston very fast, then very near to the piston the pressure will be very low, and far from here the pressure will be high. It will take a certain amount of time for the pressure to equalize itself. So which means when you try to integrate it, you would not know what is the actual function value of the P as a function of volume. So that is why you will not be able to do this calculation unless you know the process is slow and you know P as a function of P at every instant of time. So that is why we are always saying that the process has to be slow. So in this particular session we will also come across another problem where you have some discontinuity as well. So we will also discuss there what happens if there are some discontinuities, what happens if there is some non-uniformity and things like that. So now let's come back to this particular problem. So initial pressure and volume are given, so I am just writing P1 for the initial pressure. P1 is given by 3 bar and V1 is given as 0.1 cubic meters. We do not know the value of P2, but we know V2 as 0.2 cubic meters. So how can we find P2? So we know the equation for the process, so that is PV power n equal to constant. So we have P1 V1 to the n equals to P2 V to the power n. So from this we can determine P2. P2 is P1 times V1 by V2 whole to the power n. Depending on what the n is, the final value of P2 will be different. Now how do I calculate the work done? So in order to calculate the work done, I need to perform this integration. So in order to do this integration, I need to write P in terms of volume. We already know PV to the power n equals to constant. So let us solve for the first case. We know PV to the power n equals to constant, and that constant will be equals to P1 V1 to the n, and that will be equals to P2 V to the n. So I'm just calling it as C. So from this I can write equation of pressure as C by V to the power n dV, where my limits for integration will be between V1 to V2. So if I do this integration, so it will be C V to the power minus n or minus n plus 1 between the limits V1 to V2. So this gives us V to the power V to the power minus n plus 1 minus C V1 to the power minus n plus 1 by minus n plus 1. We already know C is PV to the power n, so if I substitute that back, so in the first place of C I am substituting P2 V to the power n, and in the second place I am substituting P1 V1 to the power n. So this leaves us so this is the work done in case of a polytropic process. Now if you want to use the same formula, say for the case of in this particular problem the n value is also given. For the first scenario n is 1.5, so I can solve this if I can calculate P2. So P2 is given by this equation. So for case A, what is the value of P2? P2 is P1 times V1 V2 whole to the power 1.5. So if I substitute the values, so what is the value of P2 that I will be getting? I'm getting around 1.06 bar. So you can just check and confirm me the values. Yeah, I guess the value is correct. So what do we have now? So now we have P2. So if you substitute that back, so P2 times V2 minus P1 times V1 by, and I want the answer in kilojoules. So I want the answer in kilojoules. So this is in bar times cubic meter. So I have to multiply that with 10 square, so that my answer by 100, so that my answer will be in kilojoules. So you can just quickly calculate and tell me the value. So I'm getting a value of plus 17.6 kilojoule. So again, coming to the notation, if work is done by the system, we are considering that as positive, and work done on the system is considered as negative. So here, as the gas is expanding, it is pushing the air outside, and my system is it is pushing the piston outwards. So the gas is expanding, so gas is doing work on the piston. My system is considered as a gas. Now if instead, if I would have considered piston as my system, then what will be happening to the piston? So there is a pressure force exerted by the gas from left to right, and then atmosphere is also exerting a pressure from right to left on the piston. So the net force on that should be balanced by the total displacement by the piston. So if you know the piston area, from there we can calculate delta V is 0.1 cubic meter. So from which we can calculate delta X, and F times delta X will give me the work done on the piston. So in this particular case, what would be the work done by the piston? Okay, area is not given, but even without that, you can assume that since whatever work, like who is resisting the motion of gas over here is essentially the atmosphere. So the gas is trying to expand, and atmosphere is trying to stop it. So the entire work done by the gas is used to push the atmosphere, and none of it is actually being resisted by the piston. If, for suppose, there is friction between the piston balls, between the cylinder and the piston, and in that case, then a part of this work will be used to heat up, will heat up the environment in form of friction. So then the work done on the atmosphere will actually be less than the work done by the gas. And here we are assuming frictionless, so whatever work is done by this particular gas will be the same amount of work done on the atmosphere. So as far as piston is considered as a system, we do not have any work. Is that clear? Yeah, I hope it's clear. So let's get to the next part of the question. So the second part asks you where n equal to 1. So that is an isothermal process. So if we just, I'll take forward this equation. So for in the second case, when n equals to 1, if I use the original formula that we derived previously, so we have P2 V2 minus P1 V1 by minus n plus 1. So if I substitute n equals to 1, W will tends to infinite. So this equation is not valid in this particular case because your denominator is actually tending to 0. So I need to derive this separately. So let's do that. So work done in case of isothermal process, if we just derive it. Again we use the same equation, integral PdV, but now it will be C by V. Previously it was C by V to the power n, where n equals to 1 in this particular case, between the limits V1 to V2. So this leaves us C times ln V2 by V1. So what is this C? As we have said, C is P1 V1 or P2 V2, whichever you take, times ln V2 by V1. If that particular gas is following the ideal gas law, then you can write P1 V1 as m times RT. Since the system mass doesn't change, I am not writing m1 and m2 separately. Since m1 equal to m2, for system the mass should remain constant, times T, I am writing T again. There is no subscript as 1 and 2 because in an isothermal process T1 equals to T2. So the amount of work done in isothermal process depends on what its temperature is, what its initial mass of the system is, or basically the mass and temperature of the system. R depends on changes from gas to gas, and then you have the change in volume V2 by V1. So in this particular case you can directly calculate this. So you have 3 times 0.1 times 100 to convert it into kilojoules, and then you have ln of V2 by V1, so you have just doubling of your volume in kilojoules. So what's the value you are getting over here? So I'm getting around plus 20.79 kilojoules. So in an isothermal case, you are doing work on this. Like in any particular example that you take over here, since the gas is expanding, you are doing work on the atmosphere, on your surroundings. Now coming to the third case, where you have n equals to 0, which is P equals to constant, so it's an isobaric process. So if you substitute that in our original equation, so W will be P2V2 minus P1V1 by n equal to 0, so you have minus 1. So this leaves you with, minus 0 plus 1. So this gives you, since P equal to constant, this implies P1 and P2 are same. So I'm just writing this equals to P, or maybe I can use P1. So P1 times V2 minus V1. The denominator is 1. So you already know what is P, and you already know what is V2 and V1. This 100 is just a factor to get in the corresponding units. So what's the value you are getting over here? So that's around plus 30 kilojoules. So if you see, the same gas is expanding. Depending on the process, your work is changed. So this is the work done in case of an isobaric process. So now we have 3 different processes. So work done in a polytropic process, work done in case of an isothermal process, and work done in the case of an isobaric process. So this I got around 17.6 kilojoule. Isothermal, it is around 20.79, and isobaric it's around 30 kilojoule. So you can see, unlike your unlike the case of this is what the difference between a point function and a state function, or point function and a path function is. So work is a path function. It depends on the process in which you are carrying out the work. So if work is carried out polytropically, you have a different value of work done. Isothermal, you have a different value, and isobaric, you have a different value. So work is a path function. So can you give any other example of path functions? Another path function is heat. Heat transfer is again a path function, or I'll just call it as a heat. Heat is also a path function. So it will also depend on the process. So in case of an isothermal, you have a different value of heat transfer. In isobaric, you have a different value, and polytropic, you have a different value. And if you observe it clearly, the final pressures are also kind of changing. The final state itself is changing. If somehow you maintain the initial state 1 and final state 2 as the same values, but then you reach from point 1 to point 2 in different ways, then the work done in this one and the work done in the second one will be different. So that is what a path function is. Are there any questions in this problem? I guess there are no questions, so we'll go to the next problem. So you can go through the problem, then we'll get started. So I'll also read through the problem. So air is contained in, this is a vertical. In the previous case, we have a horizontal piston cylinder as a problem. Now we have a vertical piston cylinder as problem. So the difference is, in the previous case, the piston doesn't exert any resistance, but in the present problem, if the piston has a mass, then it will resist the movement of the air. So if I consider the air inside this particular cylinder as my system, then if the air tries to expand, then it has to overcome the resistance offered by both the piston as well as the atmosphere, which was not the case in the previous example. So in the previous example, if this gas is trying to expand, it only has to overcome the resistance offered by the atmosphere, not the piston, because piston doesn't have any friction between the walls and this, so it just expands naturally, and the process is assumed to be slow, so you do not have any resistance offered by the piston. But here, because of the potential energy of the piston, you need to overcome that particular potential energy also. So let's see this. So the air is contained in this vertical piston cylinder fitted with an electrical resistor. So this is an electrical resistor that is heating the air inside this container. The atmosphere exerts a pressure of 1 bar on the top of the piston, which has a mass of 45 kg. So the piston also has a certain mass and a face area of 0.09 square meter. The electric current passes through the resistor, and the volume of the air slowly increases by 0.05 cubic meter while its pressure remains constant. So why are we saying the pressure remains constant? It's because we are assuming the process to be very slow. So if the process is very slow, which means if you consider a free body diagram of the piston, then the force exerted on the piston by the atmosphere and the air will always be equal to like the piston is moving with negligible acceleration, so the pressure of the air will always be equal to the pressure exerted by the piston on top of it. So if you consider piston as your free body diagram, so there is an atmospheric pressure that is acting from the top, and then there is a weight of the piston that is acting downwards, and then this is the air pressure that is acting upwards. So if the piston is moving very slowly, then you can consider that all of these forces are equal to each other. So essentially you will have the air pressure equal to atmospheric pressure plus whatever the weight force divided by the piston area. So which means since atmospheric pressure is anyways constant and weight of the piston is also not changing, area is not changing, so this is equals to constant. So this we have specified explicitly here, saying that its pressure remains constant, which may not be always be given, but from seeing the problem you should be able to make out that here pressure is constant. Next, the mass of the air is 0.27 kilogram, and assume there are no leakages. Somehow you have a good sealant over here near the resistor, and the gaps between the piston and cylinder are also kind of sealed properly so that you do not have any leakages. So this is my system. The mass is not leaving the boundary, so I can consider this as my system. And it is also tells you that it specifies its specific internal energy increases by 42 kilojoule per kg. So internal energy change is also given. Initially both the air and piston are at rest, and finally also they are at rest. So both the initial and final states, so only these two states are specified as rest, and even in between you are assuming that the piston is moving very slowly. The next is an interesting part. The piston cylinder material is a ceramic composite and thus a good insulator. So whenever you say good insulator, it means the heat interactions across that particular material is zero. So now piston is made of a ceramic material, as well as the cylinder is also made of ceramic material, which means the heat transfer from the air to the piston is zero, from the piston to the atmosphere it is zero, from the piston to the cylinder is zero, cylinder to the air is zero. So all the heat interactions between these elements are zero. So the only heat interaction with the air that is happening here is because of this electrical resistor. So this resistor is heating up the air. So as the air gets heated up, its temperature increases. Since pressure is constant, its volume increases, so the piston expands. So it does some work on the atmosphere. So you need to determine the heat transfer from the resistor to the air in kilojoule in two different cases. First, you have to consider only the air inside the cylinder as your system, and second, you have to consider the air plus piston as your system, and then calculate the heat transfer. So how do I start with? So we start from the first law equation. So first, even before that, I need to draw what is my system. So in this case, this is my piston and this is my heater. I'll draw my boundary something like this. So basically it will enclose everything except the resistor. So I don't want resistor inside my system. And then you have something like this. So everything except the resistor is my system. So the resistor is outside my system boundary. So across the resistor there won't be any mass transfer, so I can consider this as my boundary. So my system is defined. So this is case A. So I am considering only the air inside this as my system. So for this system, if I apply first law, so all that I have to do is Q equals to, so here we are only we are neglecting any other changes, so I am just writing, or maybe I'll write del Q equals del W plus D. I am writing in the differential form. You can also write it in terms of your deltas. Okay, so let's not get into what is the difference between D and delta. I hope you are clear with that through the lectures. So this is because this is just to differentiate between what a path function is and what a state function is. internal energy is a state function, so I am writing with a D, a differential operator. This is a path function, so I am writing just to differentiate that I am using two different symbols. Okay, now what is DE? DE is already provided in the question. So it is already given that the specific internal energy increases by 42 kilojoule, which means DE is increasing, so it is plus 42 times that is specific internal energy, so I have to multiply with the mass of air times mass of air. Mass of air is already given as 0.27 kilograms, so if I just substitute that here, I am getting a value of around plus . So now I have calculated my DE. So what is the work done? Okay, in order to calculate the work done, now I need to determine what is the heat transfer rate also. So what is the heat transfer that is happening here? So to understand the heat transfer, so as is discussed in the lecture videos as well, heat and work interactions occur only at the boundaries. So you have to see each and every boundary where interactions are happening. So what are all the kinds of boundaries that I have here? So if I write del Q, so I need to consider each and every boundary element and add them up. So can you list down them? Okay, so the first one is between the resistor and the piston, resistor and the air. Here is one interaction with the boundary, and then I have between air and the cylinder, and then I have one more with the air and the piston. These are the three areas that I can differentiate. One is between the resistor and this air, the other one is between the air and the cylinder throughout this domain, and then between the piston and the one. Like we have already discussed before, that the piston and the cylinder are made of ceramic composite, so you can consider that as an insulator, so there would not be any heat interactions across them. So I am neglecting both of these, so you will consider this to be 0, and air to piston also I am considering 0. So my entire heat transfer is only happening because of the resistor and the heater. So the question also asks you to determine the heat transfer from the resistor to the air. So this is what I am getting. So del Q resistor to air is DE, which I have already calculated, plus delta W. So now I need to find my delta W. So what is delta W? Delta W is essentially the net work done by the particular gas inside this one. So what is the work done by air or whatever gas is inside? Let's say it is air is provided in the question. What is the work done by the air? So we again resort to the old formula. So we have, it's a constant pressure process. So the work integral PdV will just come out to be constant pressure, whatever is the pressure of the gas, times V2 minus V1. So what is my pressure? Pressure is given by this particular equation. So my initial atmospheric pressure can be considered to be 1 bar. So I'm just converting everything into pascals. Plus the weight is m times c, so mass times 9.81 divided by the face area. Face area is provided to be 0.09. So this gives me this is giving a value of around 104 point, or maybe I'm writing pascals only, 104905 pascals. Now I have the pressure of air, so I can just substitute that here, and I want it to be in kilojoule, so I'm just dividing by 1000. So I have 104.905 times V2 minus V1. So it is given that the volume of the air slowly increases by 0.05. So this is essentially the delta V that is provided here. So the delta V, I am directly taking it to be 0.045. This will be in kilojoule. So I am getting a value of around 4.72 kilojoule. So if I substitute that back, So I have 11.34 kilojoule from the internal energy change and 4.72 from the work done. And this work is done by the system. It is the gas is expanding, so work is done by the air. So I am considering this to be so this will be considered positive. So if you add both of them, what is the total amount of delta Q you are getting? So I am getting a total value of Q from the resistor to the air as 16.06. So this is the first case of the problem. The first problem is you are considering only air as your system. Now let's go to the next part. So the second part asks you to consider air plus piston as your system. So now you have your container, you have your piston, and then you have your resistor also. That's positive, negative, doesn't matter, I'm just writing that. So now I'm considering air plus the piston as my system. So let's consider something like this. Let's assume this particular ones are actually inside. I just drawn it outside for the sake of clarity, but ideally this should be near the boundary, that is coming inside, like near the gap cutting the sealant again. So now let's write the first law. So you have del Q to be del W plus du, but now my system has air plus piston. The piston mass is not changing, air mass is not changing, so I can consider that as a system. I think there are no questions in that part. So now coming back here, so again, so del Q will again depend upon the total number of interactions that you are having. So if you see all the interactions, you should count from one by one from at the boundaries. So the first interaction for the boundary you have here is between the resistor and the air. So I'm writing it as del Q, resistor and air. Between air and piston is not there, which was there previously. This is not, now we should not consider this because both of them are included in our system. So the next boundary is here. So what is happening? This is between piston and the air. So I'm writing that as del Q, piston air, or maybe since air is something that I am referring to what is inside, so I'm just writing it as atmosphere, piston and atmosphere. And then if you consider this to be inside, so you have something between air and the cylinder. So that is the next one. So these are all where heat interactions happen. So similarly, your work interactions will also happen at the same boundaries. So I'm just writing them down one by one. So you have between resistor and air plus piston and atmosphere, and then you also have air and cylinder. And delta U depends only on the state, so I am essentially writing that delta U as between two things. Delta U, du happening inside the air, the change in internal energy of the air, and the change in internal energy of the piston. I am just writing it in two different ways. So I am writing du here, I am not considering the total energy, so which also includes other kinds of energies. So we are assuming that the kinetic energy changes are negligible. And so if you consider in that particular scenario, so what happens now? What is so again, like we said before, piston is made of an insulator, cylinder is made of an insulator. So this term turns out to be 0, and this term also turns out to be 0. The interaction between air, cylinder, piston, atmosphere will be 0. Only thing is between the resistor and the heater. So coming to the work, what happens to the work interaction? So what is the heater doing? The heater is only heating up this particular one. So there won't be any work interaction happening here because the heater is not causing any like the resistance when the current passes through the resistor gets heated up. It doesn't do any work. So it cannot be converted. This whatever energy is being used here inside the resistor is not being converted into raising of a weight. So you call it as heat. So there won't be any work interaction between resistor to the air. So what is happening between piston and atmosphere? So the piston is pushing the atmosphere. So there is some work done by this. And what is happening between the air and the cylinder? The cylinder volume is not changing. The air is not pushing the cylinder away or there. So there won't be any work interaction between air and cylinder. Now coming to du air. So now when you now you have two cases, case A and case B. Case A is when you consider only air as your system. It doesn't, you only depends on the initial and the final state, so this should be same as what you have from the previous case. So this value we have already calculated, is already provided as your mass of air times delta U, or I'll just write the values, the one we calculated before. So we have 11.34 that we have already calculated before, so that is going to be the same. So now what happens to du piston? So the piston, what is happening inside the piston? So if I consider piston only piston as my system, so what is happening inside the piston? So there is no heat interaction with it. So why would its temperature would not change by any value? So since it is an insulator, its temperature remains constant, and there is no heat interaction, there is no internal heat generation or anything of that sort. So du of the piston will be 0 since its temperature is not changing. So I think this part is clear. Why is this? Because T is constant and U is state function or point function. It only depends on the final state. So since temperature is not changing, your du will be 0. So now I have du air. So how do I calculate delta W piston to atmosphere? So if I consider, let's imagine, if I consider the gas inside this, the piston and the atmosphere also as my system. So basically I'll consider everything as my system. There is, the surroundings is essentially some vacuum or something, that is it's like everything that I can see in this one is my system. Then in that case the del Q, because there is nothing outside where heat can go to, if I write my first law, du cannot change, del Q cannot change. So if I consider everything in my system, so total delta W should be equal to 0. So what will happen then? So delta W between air to piston or maybe let's not complicate things further, let's put it simply. We can even say it simply. So what is happening here? The gas inside is pushing the piston and the piston is pushing the atmosphere. So what is the work done by the piston? Between piston and atmosphere, I can write it as can I say that it is equal to the same as the work done by between the air and the piston? So to say we have air to piston and piston to atmosphere should be equal to whatever is the net work done on the atmosphere, or maybe let's stick to the convention, so I'll just write plus. Actually the work done on the atmosphere will be negative, so this will actually go to the other side of the equation. Now if I consider air plus this as my system, so the work done for the air case, so in this case air plus piston is my system, so the work done by the air is whatever we have previously. So the value I'll just write it down that we have calculated before. Yeah, we have calculated here. Integral PdV, and V times have the final minus initial volumes, so that is 4.72. So I'll just write down the value. Or I can directly give you the final value. So you know that this is the total work I need to calculate, so that is just equal to minus delta W atmosphere. So I can just calculate what is the work done on the atmosphere, which will be equal to atmospheric pressure. Atmospheric pressure is a constant, and times whatever is the volume change that we will be referring to. So final volume minus initial volume. So the minus sign is just to take care of the notation, that is work is done on the system. So atmospheric pressure is 1 bar, so I'm just striking like in kilojoules, so I'm just writing 100 here, and we have delta V as 0.045, that is giving me a value of minus 4.5 kilojoule. So this is delta atmosphere. So from this we can calculate whatever is the delta W between my piston in the atmosphere. So this is my work done piston atmosphere thing. So this will be equals to negative of this, because the total should be 0, so this will be the negative of this, so that will be 4.5 kilojoule. So what is my net heat interaction? Is this work done plus whatever is the value of my internal energy change, me around 15.84. Is this clear? Yeah, I hope this is clear. So we'll go to the next problem. So the next one is a very straightforward question. So there is the heat transfer rate from a certain electric, there is a motor, and from which the heat is getting lost from the motor in this particular fashion. The expression is given as this. So as time increases, the heat is being lost. The negative sign here is to ensure the consistency with whatever notation we are following, that heat is lost from a system is considered to be negative. T is the time in seconds and Q dot is in kilowatt. The shaft of the motor, so you have a motor, so consider this as my motor. So you have a shaft is essentially the one that rotates at a constant speed. This shaft is rotating at a constant speed, and the speed is given to be, omega is given to be 100 radians per second, and against a constant torque of 80 Newton meter. So as this is rotating, say this shaft is connected to some particular wheel, or say fan, this is connected to your fan. So the fan is rotating at 100 radian per second, and the torque exerted is because of the resistance offered by the air inside your room. Because of that, there is a resistance torque that you have to overcome, that is given as 18 Newton meter. This is to an external load. It can be any external load. In case of fan, that load will be due to the drag exerted by air inside the room. So now the motor is drawing a constant electric power input equal to 2 kilowatt. So in order for this motor to run, you need to supply electricity. So this is the power that you are giving to the motor. For the motor, plot Q dot and W dot each in kilowatt, and the change in energy delta E in kilojoule as a function of time from t equal to 0 to 120 seconds. So before even doing it, so the first part asks you to calculate delta E. So you are given Q dot, W dot, and you need to calculate this. So first we'll write our first law equation. So we have, so if you want to find delta E, so let me just write the first term, Q minus delta W equals to dE. So instead of this equation, in this particular case, we are not having any flows inside or outside. So in the next week, we'll also discuss on steady state, steady flow energy equation. So now that it is not introduced, I can directly from this I can write it in this way, and I think you will be fine. So Q dot is essentially del Q del T. So I am differentiating the entire equation with respect to time, and I am writing in this particular way. So I'm just writing dE dt, or maybe I can write something like dE dt of delta E, something like this, where Q dot is your rate of heat loss and W dot is the rate of work done by the system. So my system is my motor plus shaft. So Q dot is already given to you, so I am not worried about Q dot. So what is W dot? So what are the various work interactions that I am having here? So let's say this shaft is connected to some fan. So this fan is giving me the external torque or external load. And then I have one more energy that I am giving as input. So this motor will be connected to, say, some AC supply. From which I am drawing current. So this is again work is being done on the system. So this W dot, I have two contributions. One to the external load, to cater to the external load, and other from the supply. This is the work done on the, so this is work done by the particular motor to overcome the resistance by the external load. So this will be positive because this is the work done by the system, and this is the supply that it has to take from, this is the energy that it has to take from the supply unit to, in order to run. So this will be negative. This is work done on the system. My system is this particular motor plus shaft. So if I consider this as my system, this is work done on the system, and this shaft and the work done by the system is used to rotate the shaft. So now what is the first part? So how do I calculate the load? So when you have a certain resistance torque and then you are rotating at a constant speed, so the work done will be given by, so essentially this is W dot, so maybe I'll just be consistent. So W dot is essentially the power, the rate of work done. The rate of work done against to overcome this particular load by the particular motor is torque times omega. So if you have force and velocity, we will write it as force times velocity is your power. So similarly, when you have a torque and omega, you will write it as torque times omega. So the torque is given to be 18 Newton meter and omega is again in 100 radian per seconds. So this will be in watt. So just to be consistent, the Q dot is given in kilowatt. So Q dot is given in kilowatt. So I will be writing this in kilowatt. And work done by the supply on the motor is given to be 2 kilowatt. So it is already mentioned that it takes a constant electric power input. So the work dot supply, W dot supply, is, just to be consistent with our notation, this will be negative because this is work done on our system. My system is motor plus shaft. So if I substitute this into my original governing equation, so I have dE dt. Q dot is given to be minus 0.2 minus W dot. So you have a load of 1.8 and then supply of minus 2.0. So this will give me, so the 0.2 gets cancelled and then you are left with 0.2 times e to the power minus 0.5t. So my aim is to calculate the change in internal energy over a given time between t equal to 0 to 120. So I just integrate it. So delta E will be 0 to 120 seconds. You just have to integrate this. So maybe I'll leave that, I'll just write it as a t. So the first it asks us to calculate as a function of time, then you can substitute whatever value you want. So this is 0.02 or 0.05 times t, and then you have a minus between 0 to t. So this will give you 4 times 1 minus e to the power 0.05t. So you can substitute t equals to 120 and from there you can calculate what is the delta E. So what is happening? So as the motor is continuously losing heat, even though you are supplying work and not, so what is happening finally? So as t tends to, what do you think, as t tends to infinite, what will happen is delta E tends to a constant value. So what is happening? So initially, even though motor is kind of rejecting heat to the environment and you are continuously supplying power and some power is being used to this, so if you keep, if this keeps happening, then it will reach a state where your delta E will essentially be constant. So eventually you reach a steady state where your motor temperature will be constant. The motor temperature won't be changing. So whatever is coming in, going out, and heat loss will, everything will balance each other, and then delta E will actually be a constant value. So d delta E by dt will be 0 after a certain point as t tends to infinite. So that is what we are calling a steady state. Okay. Are there any questions in this, or is it clear? Yeah, I hope it is clear. So we'll go to the next part. Next one is straightforward in some way, but then you need to have little prior knowledge on this. So basically this particular data shown over here is for the case of expansion of a gas inside an IC engine. So inside an IC engine, what happens is during different strokes, the gas inside the piston will actually expand and compress, and this particular cycle gets repeated. So what we have done is, let's say you measure the volume of the particular gas inside a cylinder, and at the same time you measure the pressure. Now we have taken different pressures and volumes. So the next part is, you don't know the process that is happening inside. So in order to calculate the work done, you need to know the process. Work is a path function. So unless you know the process that is happening, you will not be able to calculate the total work done. So the first part of the question asks you to calculate the value of n. So you assume that it is a polytropic process such that PV to the power n equal to constant, and then you need to find the value of n from this particular data. So how do you do that? How do you approach these problems? So if you are familiar with any of these Excel or any other tools, so MATLAB, Excel, Python, whatever it is, you can do any of the regression techniques that you have. In Excel, you can directly give the data, and then you can try with any of the existing interpolation fits that you can have, linear, exponential and other stuff. So in this particular case, I have already told you to use this particular relation, PV to the power n equals to constant. So instead of, I'm just writing C for the constant. So what I can do is I will just apply log of it. If I apply ln, it will be ln P plus n ln V equal to ln C. So I'll call ln P as Y. So if I just take it to the other side, so I'm calling this as Y, I'll call this as A, call this as X, I'll call this as P. So essentially now this equation is converted into a form where you have y equals to ax plus b. So this is a linear equation. So from this data you are trying to do some interpolation where you will have a linear fit. So all you are doing is a regression where you have a linear fit, and then once you determine the linear fit for this equation ax plus b, you will know the value of a. Whatever is from the value of a, you can calculate n is minus a. So once you know that, you know the particular process that is happening, and then to calculate the work done, you will use the relation that we have derived previously. So the work done in case of polytropic process is given by P2 V2 minus P1 V1. For 2 and 1, you can use the final pressure. Let's say this is state 1 and this is state 2. So we can use the pressures and volumes from here divided by minus n plus 1. So this minus n is something that we have to get from the regression that we do. So a little bit of digression here to those of you, since the session is being recorded, to those of you who are not acknowledged, or like who are not aware of the regression techniques. So just to consider this as a kind of a short introduction. So all I will do is, you have PV and I am calculating ln P and ln V. So I am just writing y is ln P and x as ln V. So from this particular data that I have given, so I'm just copying that down. So y is given as ln P. So if I just substitute ln to the base e, so I'll have So what I will be trying to do is, once I write these equations, so first I need to come up with an equation. So I have two unknowns. I have two unknowns here, a and b. So I need to find these a and b. But then I have so many equations. So how many equations I have? So how many data points? So here I have around 6 data points. So which means I have 6 equations. So I have 6 equations and 2 unknowns. How do I solve such problems? So instead of using the normal ones, what we do in such cases is we try to minimize or maximize some objective function. So we, instead of saying that all the points will satisfy, we will try to find a best estimate so that most of the points will satisfy this governing equation. So in order to do things like that, so what we do is, let's say we have a data point yi comma xi. So when I substitute that into this, so I'll calculate some loss function that is calculated as summation of yi minus axi minus pi. This I'll calculate. So why am I doing only this particular loss function and things like that? You can refer to any of the optimization courses. So we'll not go into that. So we'll assume that if I try to minimize this function, which means if most of the points are actually satisfying this particular equation, then this value of j, if always yi equal to x plus b, then the value of j will be 0. So if the particular point is not satisfying the equation, then the value of j will be little higher. So all I want to do is, when I have 6 equations and only 2 unknowns, I'll try to minimize this function so that the error is minimized. So there will be some best match of a and b that will fit the entire data that is given to me. That is my objective. So how do I do the minimization of a function? So how do you minimize j with respect to a and b? So it's like your calculus that you can remember from your +1 or +2. So if you recollect from your calculus, you have a function j. Maybe I'll write it in this way so it will be easy for you to recollect. So j is a function of a and b. Remember, y and x are not variables here. Y and x are the data points that are given to me in the problem. So my variables are a and b. I need to find a and b that will minimize j. So all I have to do is as per calculus I need to ensure del J del A equals to 0 and del J del B equals to 0. So if I calculate del J del A from this equation, it will be sigma 2 times yi minus, like if you apply the product rule, sorry, there is a minus here, times with respect to A, so there will be another minus xi coming here equal to 0. This gives me A times sigma xi square plus B times sigma xi equals sigma xi yi. And similarly I can do del Z del B, that will be 2 times yi minus axi minus bi minus b, and I am doing with respect to b, the constant is minus 1 equals to 0. So this gives me b times, here you have only a coefficient of 1, so it depends on the number of data points that I have, b times n, that will give me sigma yi. So now you have only 2 equations. So once you do this particular minimization, this is my first equation and this is my second equation. So I just have 2 equations and 2 unknowns. The sigma xi square, like I know what is yi, what is xi, so I can calculate what is sigma yi, sigma xi, and all these things I can calculate from this data, and then I can have just 2 linear equations that I have to solve for, and I'll directly get the values of a and b. So for this particular problem, if I do the summation, so I'm getting the values of, I'm getting the equations as, so you can do this later yourself, you can try this out. So the questions will be uploaded in the link that is shared in your NPTEL website. So if I substitute the values, so I'm getting my first equation as sigma xi square is 247.4264, and then sigma xi 38.3775. This will be equals to sigma xi yi. Similarly, the second equation, b times n, n is the number of data points, so here I have 6 data points, equals sigma times yi, so the summation of yi is, so these 2 equations is a linear problem, 2 equations, 2 unknowns, so it should be straightforward to solve. You can also use any calculator or anything. So if I solve these equations, so I'm getting b value of around 9.55, and a I'm getting a value of around minus 1.1996. So I'm just taking to be approximately minus 1.2. So as we have before, n is essentially minus a, so the value of n that I need to consider for this problem is 1.2. So this is the first part. So the first part asks you to find the value of n. So now we have determined what is the value of n. The second part is straightforward. So I have to just substitute that in the formula that I have. So the work done will be the final pressure times final volume minus initial pressure times initial volume by minus n plus 1. Now the units are not consistent. So the pressure is in bars and volume is in cubic centimeters. So I want in kilojoules. So I'm just multiplying from bar, you need to convert it to 10 power 5, cubic centimeter to cubic meter. So this will give me in joule. So I want in kilojoule. So I'm just dividing it with 1000. So if you do the calc math, I'm getting a value of around close to 0.642 kilojoules. So there is something wrong in the math, let me know. But other than that, I hope it's the process clear. This is only one way of doing it. You can also do it in other way is, so you have different values of pressure and volume. So all you do is take any software that you have, Excel or something. You just make a plot of it. You take pressure, you take volume. You have different volumes and you have different pressures. So as the volume is increasing, your pressure gets reduced. So it goes something like this. So initial pressure is actually some low value, and finally, so it's basically, okay, I didn't mention whether it is expansion or compression. So initial pressure is actually high. So I'm starting from here and then I'm reaching the final state here. So the process is something like this. So all you have to do is calculate the area under this graph. So if you are aware of any numerical integration techniques, you can use them. Or if you are using some Excel or something, you have different plots, different points at which our data points are given. So you approximate that in between them it will be linear, and then you calculate the area of that particular trapezoid, and then you keep adding all these areas to get the total work done. That will be a rough estimate. That could be the another way of doing. So either perform numerical integration. But that is something that is not our objective. So our objective here is to understand, okay, from a real scenario, so like the equations that we are studying here, PV to the power and polytropic processes, etc. So where are these actually coming into picture is you can collect the data, from there you try to fit it, and then you get the value of n. The value of n is straightforward in case of isothermal, isobaric and other processes, but in real processes, so why do you think the value of n is different from whatever we have assumed? So let's say you have an adiabatic process, so in or isentropic process or adiabatic process in your case, you have PV to the power gamma equal to constant. So the value of gamma in case of air is around 1.4. It's a diatomic gas, so gamma is around 1.4. So instead of 1.4, the value here is around only 1.2. So why do you think the value has changed? These are the other questions that can be answered from doing analysis like this, which we will not go into. Okay, are there any questions or is this clear? I guess there are no questions. Okay. So the next one is again a kind of an icebreaker. So there is a rigid well insulated tank. So we have a rigid tank that is completely insulated from the surroundings. The volume is specified, and the mass of air is also specified. The only difference now is you have a paddle wheel, so a wheel that is connected to it that is continuously transferring energy to the air at a constant rate of 10 watt for 1 hour. If there are no changes in kinetic energy, so K is essentially kinetic energy or potential energies occur, determine the specific volume at the final state, the energy transfer by work, and the change in specific internal energy of the air in kilojoule per kg. So what is happening here? So what is happening with the paddle thing that is rotating here? So if this paddle is rotating, so you have you can imagine this to be like you are sitting in a room. Let's say you are an observer, you do not have any interactions with whatever is happening inside the room, and then there is some fan that is rotating inside the room. So this fan is like the paddle wheel. What is the fan doing inside the air? Like what is happening? What is the interaction between fan and air? So the first thing to solve this, you have to consider a system. So let's consider a system like this. I am excluding the paddle wheel. So I'm considering this as my system. So what is happening between the wheel and air? This versus, I can also consider the another scenario. I can consider something like this. Basically, I'll take the shaft. Basically, the wheel will also be inside my system, and this is the shaft that is outside my boundary. So let's first talk about this. So what is happening in this? Okay, I've already used A and B differently. So let's use capital letters. Let's get part by part. So first question asks you what is the specific volume at the final state. So first thing is it's a rigid tank, which means the first rigid is constant volume. Whenever it says a rigid, it means volume is constant. And there are no openings anywhere, so assume that whenever the paddle wheel is connected inside the room, it is properly sealed, that there are no leakages, which means mass is constant. And whenever you say insulated, it means the heat interactions are 0. So with these in points, the first one is asks you to find the specific volume. Specific volume at the final state. So if the initial state is 1 and the final state is 2, so the specific volume at the final state is given by V2 volume by mass. Specific volume is volume per unit mass. So V2 by M2, mass is not changing, volume is not changing, so that will be same as whatever is the value initially. So this is again straightforward. So you have a volume of 0.6 and then you have a mass of 0.2. So this wouldn't be any difficult. So you can directly calculate this. So let's get back to the next part. So what is the energy transfer by work? So now again, in order to determine this, I need to say what is my system. Let's say we are talking about case B. Now if in case B that I have shown here, this one, if I am considering this entire thing as my system, so this shaft is rotating, so there is some work done by the shaft across the boundary. So always, as we have said, heat and work interactions occur only at the boundaries. So whenever some questions ask you to find heat or work interactions, you can kind of understand it by seeing what all things are happening across the boundaries. So here, what is crossing the boundary? There are only two things that can cross the boundary. One is the air between the atmosphere and the tank. Now the tank is rigid and insulated, so basically the air won't come inside, so nothing will actually cross this boundary anywhere else. The only thing that crosses is the shaft, the next thing. So as the shaft is crossing, if the shaft is rotating, then some work is getting transferred by the shaft. So why I am saying that work is getting transferred? Because if the shaft is rotating, I can tie a rope to it and I can connect it to be a mass. So if the shaft is rotating, I can convert that to a raising of a weight. So whenever this thing can be done, you say that work is being transferred across the boundary. So what is the work done? Work done is essentially your power times delta T, and the power is given as 10 watts and the time is given as 1 hour. So I'm just converting into seconds and just dividing by 1000 to convert everything in kilojoules as asked in the question. The only thing that we need to take care is the sign. The sign here is what is happening. The shaft is rotating, like the work is being transferred from the shaft to the system or the other way around. So how do I determine that? So if I connect a rope here outside the system, so this is my system. So if I connect a rope here, as the shaft is rotating, will the mass go up or down? So because of whatever is happening inside the system, the mass will actually go up or down. What will happen? You can think of this as you are sitting in a room and the fan is rotating. So the fan draws power from the whatever the mains that you are connected to. Like there is some transformer nearby from which the power is coming inside. So if your system boundary is across your room, the fan is taking power from the transformer. So work is being done on the system. So this should be a negative here, just to take care of our sign convention. And in case of this system, I have already told that it's an insulated tank. So you have del Q to be 0. So your W should be equal, minus W should be equal to your delta E, maybe minus delta W. So delta W is already negative, so this is 36 kilojoule equals to delta E. But the question asks you to find the change in specific internal energy, which is the change in internal energy per unit mass of it. So the mass is 2 kilograms. So just reading delta little e, it's delta E by mass. So mass is 2 kilograms. So this will be 18 kilojoule per kg. Okay, now let me ask the question differently. Let's say instead of case B, if we were considering case A, so what is happening here across the boundaries? So here my boundary is like between the air and the fan is kind of outside the boundary. So assume that whatever is here, this fan is not inside my boundary. The system boundary is actually outside it. Then what is being transferred across this fan to the air? So is work being done or not? So whenever I ask like work is being done or not, all you have to understand is anything that is external to the system, if it can be converted into lifting of a weight, then work is being done by it. If not, then no work is being transferred. So in this case, if you are connecting some rope to and then like something like, so if you are connecting a rope here and then you are connecting it to a mass, so as this is rotating, the mass will actually move up or down depending on the direction of rotation. So this can be converted into work only if this shaft is inside the system. So a part of the shaft, in the case B, what happened? A part of the shaft is actually inside the system. So the external effect of it can actually be considered. So if you connect a mass here, so this mass is external to the system. So always to determine whether work is done or not, your mass that you are connecting to, the hypothetical mass, should be outside your system. So the net effect of this is, as the shaft rotates, this mass will actually move up or down. So there is some work interaction. But now if you consider here, the fan plus the shaft is outside the boundary. which means this may rise up or down, but that doesn't actually depend on the system, because that is not my system. This is not actually part of the system. So the interaction between the fan and the system, that is the gas inside, is not because of work but because of heat. So what is happening here is, as the fan blades are rotating, because of the friction between the fan blades and the air inside this particular container, the heat will be generated. So here there is a work interaction, but at the boundary is here. At this you have a work interaction, but here the boundary is between the fan blades and the air, where there is no work transfer, but then there is heat transfer. So what is the amount of heat transfer that is happening should be equal to the amount of work transfer, provided your temperature is not changing at this interaction. So if the question asks you to find for case A, the only thing that will be different is your delta Q won't be 0 anymore, and this will be equal to the W, that is the power that is being dissipated, and that will be equal to 36 kJ. So but your delta E will remain the same, because this delta E is a point function. It only depends on the initial and final state. It doesn't matter what you consider and things like that. So as long as air is my system, this doesn't change, provided the temperature of the fan here is not changing. If temperature of fan is also allowed to change, then this delta A will again be split into two parts. A part of it will be corresponding to the air, and another part will be corresponding to the fan. Is this clear, or are there any queries? I guess there are no questions, so we'll go to the next problem. So this is a problem that is already discussed in the lecture video, but I just want to bring it back in the session so that we can have some interaction on this, because there are some subtleties involved in the problem. So here you have two tanks, tank A and tank B. So this is a cylindrical tank, B is a cylindrical one. So the tank A volume is given as 0.4 cubic meter, and this is a rigid tank, so the volume of tank A remains constant. And this contains an argon gas at initial pressure of 250 kilopascal. Cylinder B contains a frictionless piston, so the interaction between this and this is frictionless, and it has certain mass, and we don't know the mass of it. But it is, instead of giving the mass directly, it tells you that the mass of the piston is such that a pressure of 150 kilopascal is required to lift it. So in order to lift it, you have to overcome two things. One is the atmospheric pressure that is happening on the top. In case of A of previous problem, okay, you were showing about previous problem. Okay, is air inside the system in case of A of previous problem? Yes, my system is only air, not the paddle wheel, so I've considered only air as my system in case A. In case B, I have considered the paddle also as part of my system, like a part of the paddle, so only the shaft will be external to the system boundary. Does that answer your question? Okay, coming back to the present problem. So yeah, now we have the pressure inside this gas now has to overcome two things. One is the atmospheric pressure from the top, and it also has to overcome the mass of the piston. So the atmospheric pressure is given as, say, 100 kilopascal. So the extra 50 kilopascal is to overcome the weight of the piston. So from there you will be able to calculate the weight of piston. And this connecting valve over here is the regulating one that is slowly open. So because this is at 250 kilopascal and this is at 150 kilopascal, there is a pressure difference. So air flows from the higher pressure to the lower pressure. So this valve is slowly opened so that air moves from here to here. And this is allowed to happen till both of them achieve a uniform state. By uniform state, I mean that how long will this happen? Till the pressures in both of the containers remain same. So when the pressure inside this and this are equal, then the container, like the flow will stop, and that is what we are calling that the gas reaches a uniform state. So it has a different part. So it has basically asked you to find what is the final pressure, and second part is the work interaction for all three separate cases. So work interaction for the argon gas piston and atmosphere. So you need to consider only argon gas as your system and then calculate the work interaction. Only piston as your system, calculate the work interaction. Only atmosphere as your system and calculate the work interaction. So the first one is straightforward. First one is to calculate the final pressure. So as we discussed, the movement will happen only till the pressures in both of them remain same. So the final pressure should be equal to, finally the pressure should be equal to PB and PA. So I'm just denoting F here, superscript, to denote the final state. So finally both of the pressures should be equal and I need to determine the value of that particular pressure. So what is the value of PB? So what is happening in the tank B? This is again, we are saying that the process is happening very slowly. So as long as the process is happening very slowly, the acceleration of this particular piston is 0. So if you do a free body diagram for the piston, then it force on from the top, from the atmosphere, and the weight force and the whatever gas pressure that is happening here. So if the acceleration of this is 0, then there should be when you apply a force balance, your PB should be equals to P atmosphere plus work by whatever the weight divided by area. So this atmospheric pressure is constant and weight of piston area, these things are not changing. So your PB is constant. So the process inside the container B is an isobaric process. So this I can write it to be PB, and that is equals to, the value is given to be 150 kilopascal. So that is the first part. The second part is to calculate the work interaction for different cases. So even before solving that, so the first is the easiest one. Let's do the easiest one. So how do I calculate the work done for the piston? So what is the resistance force? Like basically the work done on the piston is essentially should be equal to the increase in its potential energy. So as the gas is moving from tank A to tank B, this piston will move upwards. So the work done by the piston, like work done by the argon gas on the piston, will be also equal to whatever this expansion process that is happening on the piston. So if you consider only piston as your system, the piston is raising upwards. So the increase in its potential energy is the work done that is done. So that will be equal to, like ideally you should write it as mg delta h. So but here instead of calculating weight, we will write it as, so this is essentially mg by a times delta h. So this I am writing as delta v. Mg by A is essentially the excess pressure. So this excess pressure is, I am just writing it as delta P times A times delta H is delta V. So excess pressure is the pressure difference between the up on the top and the lower. So here you have 100 kilopascal and from the bottom you have 150 kilopascal. So the 50 kilopascal is your delta P, and delta V you need to calculate. So how do I calculate delta V? So in order to calculate that is what the next part of the question tells you, that you can assume that the changes in state of the argon gas is related to this particular equation, PV equals to constant. So from my initial state, so we will also have a little discussion on this a little further, but for now you can assume P1 V1 is P2 V2. Initial pressure is 250 kilopascal and initial volume is 0.4. Is P2. P2 is 150 kilopascal times final volume. So if you solve this, the final volume comes out to be around 2/3 cubic meter. So delta V two by 3 minus your initial volume 0.4, that is coming to around 4/15 cubic meters. Okay, so now we are trying to understand what is work done by the argon gas on the piston cylinder. So if you consider piston, so work is being done on the piston by the argon gas. Like you have two things, like the piston is being exposed to one from the atmosphere. Atmosphere is pushing the piston downwards. So now how do I understand? So if I consider only piston as my system, so is it positive or negative? So if I consider only piston as my system, so atmosphere is trying to push it down and the gas is trying to push it up. So this is the atmosphere one and this is the gas one. I'm calling it argon gas, so let's say gas. So because of the net effect, the piston is actually moving upwards. So if the piston, what will be the work done? Like I can calculate the value here, delta P is 50 kilopascals times delta V is 4 by 15. This will be in joules, so you can calculate the value. So I'm getting a value of around 40,000 by 3 joules. So but is it positive or negative? So should I consider it positive or negative? So how will I decide that? So in order to decide that, we have to come back to our original definition of what is work done by the system. So again, coming back to the original definition, you should say that the sole effect external to the system, if it is equal to raising of a weight, then you consider that to be work done by the system. If it is the other way, then you consider it to be negative. So what is the sole effect external to the system? So here what is happening is, if you are considering your datum level to be this, so this is my datum or my reference level, and the piston is actually moving upwards. So external to the system, for example, if I connected this to a pulley and then I connect it to a mass, so this entire pulley and mass, whatever is there, is external to the system. So if I want to raise this piston, what should happen? This particular mass, should it go upwards or downwards? So for this piston to move upwards, this particular mass should actually move downwards. So from our definition, work is done by the system only if the mass moves upwards. Now since mass is moving downwards for this to move upwards, which means this is work done on the system. So we should consider this to be negative. Now doing the same for the atmosphere. So if you calculate the atmospheric work done on the atmosphere is again the same thing. So we have a pressure times delta V, but then the pressure here will be the atmospheric pressure. So the atmospheric pressure is given as 100 kilopascals. So I'm just writing in bars times your delta V. I've already calculated that. So what would that turn out to be? That is giving me a value of around. So again, the piston as well as the argon gas are trying to push the atmosphere outwards. So this will be a negative work. This is work done on it. So I'm just writing minus now. So this will be minus 80,000 by 3. So now what is the work done by the argon gas? So combine all of them should be equal to 0. So work done by the argon gas is negative of whatever is the work done by the atmosphere and whatever is the work done by the piston. So that will give me a value of around 40,000 joules. So this is straightforward. Now let me ask the question. So here we have already told that the state of the argon gas is related to PV equal to constant. So if we have PV equal to constant, we have seen this before, that this is the equation of a isothermal process. So when you have an isothermal process, you can write PV equals to constant. So previously when we derived the work done in an isothermal process, so what is the work done in an isothermal process? In case of an isothermal process, the work done is given by P1 V1 ln V2 by V1. So this is the work done in an isothermal process. So when you have P equal to constant, this is the equation that you can also use. So if you substitute this equation, so what will happen? The P1 is already given to you. V2 by V1. V2 I have already calculated as 2 by 3. So what is this value coming out? So I am getting this value to be around 51,082 joule. So now if you see this, the interesting part here is, if you assume this equation PV equal to constant, then you have an isothermal work of around 51,082 joules. But then from whatever we have, like the work done on the piston is around 40,000 by 3, work done on the atmosphere is this. So whatever is the work done by the argon gas, it has to go to the piston or that, so it has to overcome the resistance by the piston and it has to overcome the resistance by the atmosphere. But the resistance from the piston is only contributing to around 40,000 by 3 and from atmosphere is only around 80,000 by 3. So the total resistance that will be around only 40,000. So where is this difference going? So this is where we have the importance comes from the definition of the work done. So whenever we are calculating this work done, we have assumed that it is a fully resisted process. So whenever you have a fully resisted process, that is when only you can account for this. So if you have a partially resisted process like the one here, this is an example of a partial resisted process. So why am I calling it partially resisted? It's because of the presence of the valve here. So initially this is at 250 kilopascal and this is at 150 kilopascal. Now as the valve is open, this 250 will actually become to 200 and then this will still be 150. So there is a discontinuity at the valve. So there is a delta P across this valve. So which means you cannot directly use this equation. So what does P mean? Should I calculate that? Should I take the value of pressure from tank A or tank B when I am doing this work interaction? To calculate this, like we have defined, you have to do the integration. But then as volume is changing, you do not know what is the actual pressure that you need to consider. So in case of this partially resisted process, you do this indirectly. Indirectly what you would say is, you only calculate the amount of work that you can extract from the system. If I consider the argon gas inside both tank A and tank P as my system, the work that I can extract from this system is only through this piston assembly system. So if this is expanding, if I connected, okay, maybe I'll just use a different color. So if I connected this to again a pulley and then I can connect it to a mass, if this piston is moving up, so if this is connected something like this, so if this piston is moving upward, I can displace this mass. So this is the only useful work that I can extract. There is a pressure difference across the valve that there is a pressure difference, but I cannot use that pressure difference to generate any displacement work that I can calculate. So this difference here between this 40,000 and 51,000 is essentially that is wasted in order to ensure that you have a reversible process or a fully resisted process. So or maybe to put it simply, imagine if you do not have the valve, what will happen? If you do not have the valve, you just connect it directly, like you suddenly open the valve and just leave it open. What will happen is like this gas will continuously come in and this piston will suddenly go upwards. It's just like you have a high pressure cylinder and you just open the, like you have a Coke bottle and then you suddenly open the cap, everything just rushes out. That is the same thing that will happen if you do not control this valve. So now in order to have a slow process for which all these equations have to be valid, only you need a slow process. So in order to ensure a slow process, you need to open it slowly, like you open the cap very slowly, so that this rushing won't happen. So in order to open it slowly, you need to continuously spend some energy, and that energy is what this difference is accounting for. Okay, so if in an exam or in your test they ask you to find the work, so this is the work that you should be calculating, not this one. Simply because in order to calculate this, in order for this equation to be valid, you need to have a process where you know P at every point throughout the process, which is something that we do not know here because of the presence of this discontinuity. Okay, is this clear? Or are there any questions? Okay, I guess there are no questions. We'll go to the next problem. The next one is again a straightforward problem. So here you have a piston cylinder device. Okay, I haven't mentioned it as to be vertical, but by default you assume it to be a vertical one. You can also say that it is horizontal, but for now, okay, maybe I'll just say this piston is resting on stops. So you have a piston and then there are some stops here. So the piston is actually resting on some stops. So it is a vertical piston cylinder assembly. Initially it contains 3 kg of air at 200, so mass is given to be 3 kg of air. So assume there are no leakages. So the initial pressure is also given 200 kilopascal and initial temperature is given as 27 Celsius. So I'm just writing in Kelvin. And ensure that you always convert temperature to Kelvin when dealing with the problems, since most of the time the temperatures that we deal, all these equations, the temperature should be in absolute units, not the Celsius. So ensure you always convert them into Kelvin. it says that the mass of the piston is such that a pressure of 400 kilopascals is required to move it. So initially it is resting on the stops, so there is a reaction force from the stops that will balance the weight of this particular piston. But what are we doing is we are heat is now transferred to the air. So let's suppose you have okay, maybe not a candle, let's say you have some fire or something. Okay, this doesn't look like a fire, but okay, maybe I'll just put heat here. That would be the easy way. So you have some heat that is being added to the air inside this one. So as you add the heat, the temperature here increases. And then what happens? Gradually, after a certain point, if the expansion is sufficient enough to overcome the weight of the piston will start moving upwards. So what they are saying is the piston will move upwards only if the pressure inside this is 400 kilopascal. So until the pressure inside reaches 400 kilopascal, it won't move. Now it says heat is now transferred to the air until its volume is doubled. Okay. So now you are continuously adding the heat till the volume is doubled, which means the piston is actually raised upwards. And the final volume is actually double the initial volume. Let's say V1. I'm not calculating V1, I'm just leaving it that there. We know that the V2 is 2 times V1. This is the only information that is okay. Let's say for now the final volume is double the initial volume. You need to calculate the total work done and total heat transfer to the air. Okay, so how do I start the problem? So it's always better to conceptualize what is happening, like what is the process that is happening, like either through a graph or understand what is happening intuitively, and then you attempt to solve it. So let's say you want to try it on a graph. So what is happening in the process? So if I plot it on a graph, so let's say I choose P and V as my y and x coordinates. So initially there is certain volume V1. So now what is happening? As the heat is getting added, temperature will actually increase. So maybe I'll also draw P versus T, or PV is fine. So as temperature is increasing, initially until the pressure reaches 400 kilopascal, this piston won't move upward. This will be like the weight of the piston is so high that till the pressure inside reaches 400 kilopascals, this won't rise. So till that particular point, you can consider this process to be a constant volume process. So in a constant volume process, if you are adding heat, its temperature will increase. So if you assume this particular air to be an ideal gas, following ideal gas equation, mass is constant, so your number of moles is constant. So in case of a constant volume, if temperature is increasing, then your pressure should also increase. So initially you are at some particular point pressure. The pressure is given to be around 200 kilopascals. Let's say this is in kilopascals, and then it will expand up until 400 kilopascals. So you are starting from an initial volume somewhere V1, and then you will go till 400 kilopascals. Still this particular arrow here, till you reach this particular point, you will be a constant volume process. Once you reach that particular point, and once the piston lifts from these stops, then what is happening is it's actually raising against the atmosphere. So there it's again a constant pressure process, like we have discussed previously. This is a very slow process, so you can assume that the acceleration of the piston is 0, and then the pressures should balance on inside and outside, which means it is since outside pressure and mass of the piston are constant, the pressure of air inside will also be constant. So that is a constant pressure process. So how long that the process happen? The process happens till volume is doubled. So let's say you reach another volume here, that is 2 times V1. So I have 3 states. The first state, initial state, and then there is an intermediate state, and then there is a final state V3. So 2 to 3 is a constant pressure process, 1 to 2 is a constant volume process. So now what can we say about this? So this is the one state. So from this to the second state is a constant volume process. So I'm just writing delta V equal to 0. In constant volume process, what is the final pressure? I know the final pressure. If the final pressure is 400 kilopascals, so what is the final temperature? So constant pressure or constant volume process, P is proportional to T. If pressure is double, then your temperature will also double. So from 300 Kelvin, it will become 600 Kelvin. And from 2 to 3, it is a constant pressure process. So I'm writing delta P equal to 0. So in a constant pressure process, what will be the final pressure? Equals to the initial pressure, so that is 400 kilopascal. And what is happening to my temperature? My temperature will be proportional to volume in case of a constant pressure process. It is already given in the question that the volume is double. So if volume is double, then your temperature will also double. So your final temperature will be from 600, it will be double to 1200 Kelvin. So now I have my states. Now how do I calculate the work done by air and total heat transfer to the air? So what is the net work done? Net work done is essentially the area under the PV curve, or so what is the area under this curve? So why I am saying it is area under PV curve is because work done is defined as integral PdV. So integral PdV is like integral f of x dx. So this is essentially the area of the area covered by f of x in that particular domain. So in this case, area is the final pressure P2 times 2V1 minus V1. So P2 times V1. So how do I calculate V1? We use ideal gas equation. So if you use ideal gas equation, P1 V1 equals to m times RT1. So from this relation, I can get V1 as mRT1 by P1. P2, I already know the value of P2 by P1, 400 by 200. Mass is something that I know. Initial temperature is also known. So the R value here. So what should be the value of R that I should be using? So it's not like the 8.314 that you might have already been used to. The 8.314 you should use in terms of moles, but here we are talking in terms of kilograms. So the R value you should convert it into the kilograms. So 8.314 is joule per, instead of kg you will have moles. So I'm just converting to, so I have to divide it by the molecular weight. So the molecular weight of air you can consider like nitrogen is the dominant, so you can approximate it to be 28.8. It will be in grams, so I'm just converting into kilograms. So this will be the value of R that you should be using, which will come out to be around this is coming around 289 or something joule per kg Kelvin. So this is the value of R that you should be using here. So like you can change this weight, and that will depending on the molecular weight of the gas, your R value will actually change. So what is the value you will get here? So I'm getting around 520 kilojoules. So I'm just dividing by 1000 to convert it into kilojoules. So this is the work done. So now how do I calculate the heat transfer? This is the first part. So Q net is essentially your W net plus U net from your first law. So this could be one way. So how do I calculate U net? U is a state function, so you don't have to know like it has actually went through the process 2 or something. All you need to know is what is the initial state and what is the final state. My initial state is at 1 and my final state is at 3. I don't even have to know what is the 2. Like even if I go in this particular path, even if I go in this particular path, it doesn't matter. Your U net will actually be the same. So maybe delta U. I should be writing delta. Delta U net will actually be the same. So what is the delta U net? We already have that as mCV delta T. Delta T I am writing as T3 minus T1. M is already known. What is the value of CV? If you have gone through the lecture videos, in case of pure substances, you can consider air as a pure substance. So M is already known. CV I can write it as R by gamma minus 1. I can assume that it is a diatomic gas, like mostly nitrogen. 1200 minus initial is 300. So if it is a diatomic gas, the value of gamma is around 1.4. So this will be 0.4. So just to convert into kilojoules. I'm getting a value of around 1950.75. So the net heat transfer will be sum of these two, the work done and the net change in internal energy. Here the gas is expanding, so the work done is by the system, so you can consider that to be positive. So Q net is 520 plus this. That is coming to around 2470.75. Alternatively, you can also see that the first process is an isochoric process. So if it is an isochoric process, the work done in this case is 0, like volume is constant, so PDV is 0. So the net heat interaction will be mcv delta T, that is equal to internal energy change. The second case is an isobaric process, so the heat change you can directly write as mcp delta T. So you can directly calculate it as delta Q net is m times cv times T2 minus T1 for the first process. Second is an isobaric process, so you can write mcp T3 minus T1. Sorry, T3 minus T2 between 3 and 2. You can solve this way and you can check whether you are getting the same answer as this. I'll leave that as an exercise. Okay, so are there any questions in this, or is it clear? Okay, I guess you're clear with this. Okay, we'll come to the next problem. So you can go through the problem. So basically you have again a piston cylinder assembly, but then here you have the piston in a horizontal position, so you don't have to worry about the gravitation for the piston, like the weight of the piston you can neglect for now. If there is no friction between piston and the cylinder, you don't have to worry anything about the piston, so it is not offering any resistance. It has some fluid system here as shown below. It is frictionless and it is held down against the fluid due to atmospheric pressure. The only thing that is holding this is atmospheric pressure acting from this side. The steering device, this particular thing is a steering device that is turned around 9500 revolutions with an average torque against the fluid of 1.25 Newton meter. So the torque is given and the rotations is also given. Meanwhile, now what is happening, now as this rotates, this thing stirs the fluid inside. So as we decided previously, I consider air as my only system. There will be some heat interaction, which means you are indirect. You can think of this as you have some cup of tea or something, and then you have a spoon and you continuously stir it. You see that after a certain time, if you have a steel glass and then you stir it, the steel gas get heated up. So why is this happening? You are doing work by kind of rotating it, but then how is it getting converted to heat? Is again because of your internal resistance between the fluid and the spoon. The same thing is happening here. As this wheel is rotating, your air is getting heated up. So as it gets heated up, it expands. As it expands, it pushes the piston towards the left. So the piston expands, like the gas expands, and the piston moves by around 0.6 meters. So that is also given. So find the net work transfer for the system. What is my system? The system is the boundary that I have shown here. So for this system, you need to calculate the net work done. Again, you use the first law, or you can directly calculate the net work done. So what are the different resistances that I am overcoming here? So the net work done, or maybe I'll write it as the rate of work done. So will be what? So there is some gas expansion by the gas, so there is the expansion by the air inside the cylinder. So what will that be? So which process? Can I consider this to be an isobaric process? Is the pressure constant? The piston is frictionless, and again you assume the process is slow. So the atmospheric pressure is the only pressure that is happening here. So you can consider this to be an isobaric process, right? So if you consider this to be an isobaric process, what is the work done? P times delta V. I'll just write displacement work. Displacement work. P times delta V. So how do I calculate delta V of the gas? So we know the area of the piston. Like the diameter of the piston is given to be 0.65 meter. So we know the area of the piston and we know how much it displaced. So delta V is A times delta X. So your pressure is atmospheric pressure, since you are assuming it's a very slow process, and area is pi times d square by 4 times your delta X. So atmospheric pressure is given to be 101.3 kilopascal and diameter is given to be 0.65 meter. Delta x is given to be 0.6 meters. And air is expanding, so this is a positive work. So if you substitute this, what is the value you are getting? So I'm getting a value of around 20.168. Just writing in kilojoule. So this is for the displacement work. So is that it, or there anything else? Now external to the system, what is happening? This particular weight is again raising. The stirrer device, whatever is it, is again being turned, and because of which is getting raised. So what is happening over there? So it's like the same we have discussed previously. So what should I do for that? So I have a torque. The torque is because of the fluid. The torque is against the fluid. As it is rotating, it is overcoming the friction of that. So you have a torque of 1.25 Newton meter, and then my omega is 9500. It's like this is not omega, essentially omega times delta t is 9500 revolutions. So one revolution is 2 pi, so this will be 9500 times 2 pi radians. So the work done by the, I'm just calling it stirrer, will be this torque times tau omega times delta t. So that will be around, so just substitute it. .612 kilojoule. So is it work done on the system or by the system? So who is doing this work? Is you are supplying this work to the air indirectly. So this is a negative one. So what is the net interaction? This is expansion of the positive one, and then you have the work that you are doing on it from the stirrer. So then it will be coming to around minus 53.994. This is clear, or are there any questions? So if there are no questions, I have a couple of MCQ questions. Those are very straightforward, so I don't want to discuss much time on that. Okay, if this is clear, then the MCQ questions are kind of very straightforward questions, just to kind of have some discussion. So you have you have a perfect gas. So what is a perfect gas? A perfect gas is the one that follows your kinetic theory of gases. So you have your P as given as 1 by 3 mNc square, temperature given as the 3 by 2 kT and stuff like that. It's like the internal kinetic. So the internal energy of a perfect gas depends on what? Does it depend on the specific heat, temperature, pressure, and enthalpy? Which of these does it depend on? So what is the relation for internal energy? Like let's say specific internal energy, or you can say internal energy to be mcv delta t, or if you consider t equal to 0 as your reference, this will be mcv t. So can I say that internal energy of this particular gas depends on temperature, specific heat and pressure, temperature, specific heat and enthalpy, temperature, specific heats, temperature only? What does it depend on? So what is Cv for a perfect gas? Cp we can again write in terms of a gas constant as R by gamma minus 1. So R is some gas constant that will only depend on the type of a gas, like it only depend on the molecular weight of the gas. If your gas changes, then your R value changes. Gamma is again depending on whether it is a monoatomic or diatomic gas. So which means this is only a function of temperature. It doesn't depend on the specific heat. Essentially the specific heat again will depend on indirectly on the type of gas. So you don't have anything to deal with that there. So when you are asked something like this, when you have a perfect gas, its internal energy only depends on the temperature. So only if the temperature, like if your state changes, when its temperature changes, that's when your internal energy changes. I hope this is clear. The next one is again the same question, a slightly modified one. So we have a polytropic process. So in a polytropic process, we have already derived what is the work done. Now the question is to determine what is the heat transfer. So in a polytropic process, what is the work done? So how do I calculate it? Let's say you have a process from P1 V1 T1 to P2 V2 T2, and then I know that P1 V1 to the n equals P2 V2 to the n. So how do I calculate the heat transfer in such a case? Heat transfer is given by work done plus change in internal energy, and this change in internal energy is given by let's assume unit mass system, so just to make things easier, mCv/dt. So how do I calculate delta T? So my relation is here in terms of pressure and volume, so I have to first convert it in terms of temperature so that I will be able to calculate this. So if I do that, so let's say I use ideal gas equation, P1 V1 equal to m times R T1. So I am replacing P1 with T1 by V1. If I do that, if this is equation 1, this is 2, if I substitute 2 in 1, what am I left with? So P1 will be replaced with T1 by V1 times MR gets cancelled on either side, so V1 to the n is T2 by V2, V2 to the power n. So you have T1 V1 to the power n minus 1 is T2 V to the power n minus 1. So what is my delta E? Is Cv times T2 minus T1. So Cv T2 can be written as T1 times V1 by V2 to the power n minus 1, or we will stick to the normal. We'll just write it as Cv, I can write it as R by gamma minus 1. If you consider a unit mass system, R times T2 is P2 V2, R times T1 is P1 V1 by gamma minus 1. Maybe we don't require this, so I don't want to confuse you. This is just for simplicity. So P1 V1 is given as RT1 and P2 V2 is given as RT2. And we already have the work equation before, so work done is given by P2 V2 minus P1 V1 by minus n plus 1. So my heat interaction will be sum of these two. So if I just do this math, it's just a little bit of rearrangement. I'm just taking 1 minus n out so that I can put it in the form that is given in one of the options. So you have the answer over here. So this is just a straightforward mathematical manipulation, so I don't have to discuss much. Are there any questions, or is this clear? Yeah, these are the questions I have for this week. If there are no further questions, then we can end the session for this week and we will meet in the next week. Yeah, I guess there are no questions, so we'll conclude the session for today. Thank you for joining. We'll meet next week at the same time, Saturday 5 to 7. We'll discuss more problems on first law, and maybe we'll also discuss some concepts as well. Thank you all for joining.